So far, we've covered several key operations on and between generating functions. First of all, in episode 2, we added, subtracted, and differentiated them. In episode 3, we integrated and composed them. So for example, we remember from that episode that the sum as n goes from 0 to infinity of thing to the n, whatever thing may be, replacing x in this situation, is equal to 1 over 1 minus thing as long as the size of your thing is less than 1 if you're trying to plug it in as a number, or again, a thing. So this is the idea behind composition, and we'll be using that today as well. But there's one operation that's so elementary with normal numbers that we've seemed to have overlooked between generating functions, and that's multiplying them. And you might first wonder, how do you multiply two infinite sums? This seems ridiculous. And we'll show you in this episode how multiplying two generating functions, which once again are ways of encoding a sequence of numbers into an infinite sum as coefficients of that polynomial, of that infinite sum polynomial. And we'll show you that multiplying two generating functions together yields an operation on sequences called the discrete convolution. So, how are we going to do this? Let's start with two sequences, a naught or a sub n and b sub n. And they're encoded by the generating functions a of x and b of x respectively. And again, this would be the theoretical closed form that I highlighted in green on the left. This is the generating function form. And then the long form on the right side is over here. So you have a naught plus a1x plus a2x squared, a3x cubed, and so on. O of x to the fourth, as we remember before, just refers to all terms of order x to the fourth and higher, grouped together for the sake of brevity. So then the same thing we have with b naught, b1x, which has b1x to the first power, b2x squared, b3x cubed, etc. And also don't forget that with the zero terms, you really have an x to the zero hidden here, but it's not very important for actual numerical meaning. So how do we multiply these two sums together? There's a lot of terms to keep track of. In fact, there's infinitely many. So you might wonder how, again, you have to keep some organization here, right? So what we're going to do is we're going to, in fact, keep track of terms of equal order. So x to the first power, x squared power, and we're going to group them together. So let me show you what I mean. First of all, let's start with x to the zero term. How many different multiplications are possible in these two infinite sums, such that we get terms of x to the zero? Well, there's only one. We can simply only multiply a naught and b naught. And that gives us, of course, a naught times b naught. I'm going to try and write this much more clear, like this. That's a naught, b naught. That's our first term, and that's the x to the zeroth term. Okay, now let's add this to the x to the first power terms. What could these be? First of all, you can multiply a naught by b1x in the other multiplicand. So you get a naught b1, like this. And then you can add that to the next possible multiplication, which is a1x times b naught, correct? To give you x. So you have a1 b naught. Excuse me, I'm going to change that to the color we've been using. a1 b naught, correct? Times x to the first power. Then you have the x squared terms. So for example, the first thing you can start with is going to be, I'm going to try and find some more colors here. So a naught and b2x squared, because we're on square terms. So you have a naught b2, which is going to have an x squared next to it. Then the other x squared terms we can have, well, we can multiply, right, a1x to the first power by b1x to the first power. So we have a1x and b1x. And so what we get here is we get a1, b1 as our coefficients. And we can add that to the final multiplication we can make, which is going to be a2x squared and b naught, like this. So you have a2 b naught. And each of these terms adds together and is factored out with an x squared term, like this. And then let's just do the x cubed just one more time, just so we can get some better ideas. First of all, we can multiply a naught and b3 x cubed to get an x cubed term. So you have a naught b3. Then we can add that to the next term, which is a1x multiplied by b2x squared, right? Because those give us x cubed total. So that means we can do a1 b2. And then we can also do b2x squared times a1, or sorry, we just did that one. I meant to say a2x squared b1x. It's already getting a little confusing, so you can see how it's important to keep track of this with different colors. So you have a2 b1, because that way you have another x cubed term. And is that it? Well, no, it's not, because we have one more term. If you can guess what that is, it's going to be a3x cubed and b naught. And so what we get is we get a3 b naught like this, and that's the final term, and you have x cubed factored out each of those terms. Then we can just add O of x to the fourth, because all the terms are going to be order x to the fourth and higher. Now, what do you notice about this result so far? We notice that there's a beautiful pattern. It looks like for every coefficient of x to the n, there's n plus 1 total additions being made. And moreover, what you see is that they're lined up in an interesting order. You can see that in each of these sums within the coefficients, the a naught is increasing. So the an sequence is increasing in number, and then the b naught is decreasing. So b2, b1, b naught, while we have a naught, a1, a2. And for example, in the cubic case, you start with a naught, then a1, a2, a3, and this mirrored by the b3, b2, b1, b naught terms. So it looks like kind of, and this is an interesting way of describing it, but maybe the an sequence is lined up in correct order, and then the bn sequence is lined up in reverse order, and then we line them up against each other and just multiply down the columns that we get, and then add them all together at the end. So this weird anti-parallel multiplying column structure adding together pattern seems to be manifested in the result. And mathematically, this is called the discrete convolution of the two generating functions. It's the product of them. And the result that we can write mathematically is the following. Right over here. We write instead of a multiplication sign, we do a star instead of a dot, but it really doesn't matter in the case of generating functions. You get a of x star b of x, or alternatively a star b of x, is another function c of x. And the c of x has a generating function of the following form. The sum as n goes from 0 to infinity of the quantity sum as I goes from 0 to n of a sub I, b sub n minus I, which shows us that little anti-parallel structure. As I goes up, ai goes up, but then we have n minus I, so when I goes up, this term goes down. And then you have x to the n hopped on to the side. And you can verify yourself mathematically and looking at the pattern here, maybe for the x cubed term. So set n equal 3 and then write this out and see if you get the exact same thing. You should. Then, what does this mean? Using the notation we learned at the end of last episode, we can say that the coefficient of the x to the nth term, which is read as square brackets as coefficient of x to the nth term, in spiral brackets we have the convolution or the generating function, a star b of x. Then the coefficient of the x to the nth term is going to be simply what we have in parentheses over here in a green box, and that's just reproduced down here. The sum as I goes from 0 to n of a sub I, b sub n minus I. And so you might wonder what we would do here. Well, let's play around with some different functions and see what we get. What if the second sequence, the b sequence, was just simply all ones? So we say b sub n, or n minus I, is equal to the 1 sequence, which looks like this, all ones. Then what do we get? Well, then what we get is that the coefficient of the x to the nth term in this generating function, a of x convolved, right, with the generating function encoding the 1 sequence with the variable x. With that, we get simply the sum as I goes from 0 to n of a sub I times 1, which is just a sub I. But what do we know about the 1 sequence? What generating function encodes the 1 sequence? Well, it's the geometric series, 1 over 1 minus x. So I'm going to write this 1 over 1 minus x. And so what you really get is an interesting result. You get that the coefficient of the x to the nth term I have this somewhere here in my environment. Not there, that's a spoiler. Okay, looks like I missed it here. But it looks like what we have is that the coefficient of the x to the nth term in the generating function a of x divided by 1 minus x, which is really just multiplying it by 1 over 1 minus x. I'm going to call it, hitting it with a 1 over 1 minus x to be a little more enthusiastic now. And that's going to be equal to the sum as I goes from 0 to n of a sub I. And you can see how this might be an interesting way of computing the sum of the first n, or first n plus 1, I guess in this case, terms of a sequence. And you can check out my sum of first and natural numbers 3 ways video, which is going to be carded right now, to see this motion in action. So now that we have this result, which is also an interesting little offshoot of the main idea of a convolution, what if we chose a of x to also be the geometric series? So what if a is equal to 1 over 1 minus x as well? Then what do we get? We have 1 over 1 minus x squared now, like this, is going to equal the sum, by the formula we have for convolutions, of n going from 0 to infinity of, in parentheses, a sum as I goes from 0 to n of what? Well, our AI sequence is simply going to be 1, so a sub I equals the 1 sequence, and b sub I, no matter what b is also equal to the 1 sequence, so we just have 1 over here. And you multiply that by x to the n on the side. Then what is the sum as I goes from 0 to n of 1? Well, that's just a constant, and that's you're just adding 1 together a total of n plus 1 times, because you're going from 0 to n, which means that the result here becomes n plus 1 as such. So then 1 over 1 minus x quantity squared should equal the sum as n goes from 0 to infinity of n plus 1 x to the n. Now, we've seen this before in episode 3 on differentiating, right? Or episode 2, excuse me, of differentiating. We knew that the derivative with respect to x, so d dx of the geometric series, 1 over 1 minus x, is equal to 1 over 1 minus x squared. All right, you can verify this with the power rule and then chain rule. Then that means that if we take the derivative of the geometric series directly, we should get the exact same result as above with the convolution. So we get d dx, it's a terrible d dx of the sum as n goes from 0 to infinity of x to the n. Well, that's simply by linearity the sum of the derivative. So you can switch these two around. That's what I'm going to do right now, like this. We get a sum of the derivative with respect to x of x to the n, which we know is going to give us the sum as n goes from 0 to infinity of nx to the n minus 1. Now, what does this equal when n is 0? Well, it's equal to 0. So there's no point in including it. We might as well just start with n equals 1. But if we want to re-index this now to start back at 0 to make sense and to have no 0 terms, what do? Well, if n equals 1 has to become n equals 0, you just replace every n with n plus 1, as we've done before with re-indexing. So this is equal to the sum as n goes from 0 to infinity of n plus 1, x to the n plus 1 minus 1, which is x to the n. And look, this is the exact same thing we have over here by our convolution method. So I'm going to reproduce that right over here to show you that these are in fact the same thing. So that's pretty cool. We know that works. Now, what if we were to convolve 1 over 1 minus x, or hit it with itself a multiple number of times? So 1 over 1 minus x star, 1 over 1 minus x star, on and on and on, until we get the final 1 over 1 minus x starred. All right, so if we convolve it with itself, let's say k times, then we should, in theory, get the result short form to be 1 over 1 minus x to the kth power. What generating function might this form have? And you might understand that to compute this with convolutions is itself a convoluted computation to make, pun intended. So let's use the idea of derivatives, right? Because we saw the derivatives seem to work a little bit in terms of making this problem easier, and it gave us a similar result. So let's leverage what we know about derivatives of generating functions to compute the generating function of 1 over 1 minus x to the k, also known as the repeated convolution of the geometric series with itself k times. So we can look at this from the following perspective. We know that the derivative, the kth derivative perhaps, of the geometric series is going to be what? Well, this is 1 over 1 minus x, and 1 over 1 minus x is also the same thing as writing 1 minus x to the minus 1 power. Then the kth derivative means we keep hopping down minus 1, so it becomes minus 1 times 1 minus x to the minus 1 minus 1, which is minus 2, and so on and so forth. So what do we get after k of those kind of iterations? Well, we start with minus 1, then we have minus 2, minus 3, so on and so forth, all the way up until, and this is where you have to be careful, but you get minus k. And then what you get after this is 1 minus x to the power of minus 1 minus k. And you can see how this is iterative, because if you had just started with the derivative of 1 minus x to the minus k, you get minus k, 1 minus x to the minus k minus 1. But don't forget, there's a mistake there, because we need the chain rule because we have that minus in front. And since we took the derivative of k times, we just have to throw in a minus 1 to the k term. And ignore this for now. This is not to be looked at yet. So we have this. Now, look what you see over here. Minus 1 times minus 2 times minus 3 all the way up to minus k. That's k multiplications, and you have k minus 1s in there. So you can do minus 1 to the k, and look, you just get k factorial. And notice that this minus 1 to the k can cross out with this minus 1 to the k. So you get, ultimately, k factorial 1 minus x to the 1, or to the minus 1 minus k, like this. In effect, what you're saying is this is equal to k factorial over 1 minus x to the k plus first power. All right? And that's going to be the same thing as saying the kth derivative of the geometric series. So if we want to find the generating function of 1 over 1 minus x to the k plus 1, all we have to do is take the kth derivative of the geometric series and divide by k factorial. So you get 1 over k factorial dk dx to the k of the geometric series, which we know is a sum as n goes from 0 to infinity of x to the n. Now, notice how by linearity and by the fact that 1 over k factorial does not depend on n in the summation, we can just hop these and switch their order. So this is equal to the sum as n goes from 0 to infinity of 1 over k factorial dk dx to the k, which I'll reproduce just like this, x to the n. All right, so then what is the kth derivative of x to the n? This is just a repeated application of the power rule. So you get n goes from 0 to infinity of 1 over k factorial, and this is where you have to be careful again, because you have x to the n, which means you have to multiply n first, then n minus 1, n minus 2, so I'm going to write n, I'm going to write a nicer n, n minus 1, n minus 2, all the way down to what number? Not n minus k, because that's going to be the exponent result in the top. It's going to be n minus k plus 1 for that reason. So n minus k plus 1, then you have the result x to the n minus k. Because notice how if you were to just differentiate x to the n minus k minus 1, you'd have to have that hop down and then subtract 1, or plus 1, sorry, up here. Then to differentiate this on its own, you'd have to hop this exponent down to get n minus k plus 1, and then subtract 1 off that and get n minus k as a result. All right, good. So now notice how for this geometric, or not geometric, but generating function, n equals 0, well, that just gives us 0. N equals 1 gives us 0. And in fact, every term all the way up to n is equal to k minus 1, and including this term, these are all going to give us 0. So it's really no point in starting n equals 0 in this bottom bound. We can just write as well n equals k to give us 1 as our first value. And this is similar to what we did with the 1 over 1 minus x quantity squared just a few minutes ago. So now we do reindexing. If we want to start at 0, we have n equals 0 now to infinity. What should we do? Well, we replace every instance of n with n plus k. So I'm going to write this in red. N replaced by n plus k. So you have 1 over k factorial does not remain changed because there's no n there. Then you have n plus k times n plus k minus 1 times n plus k minus 2 all the way down to n plus k minus k plus 1. So n plus k minus k plus 1, which is simply going to be equal to n plus 1. So I'm going to write that down. And then, well, that means x to the n minus k becomes x to the n plus k minus k, which gives us x to the n. So x to the n power. So you can see how we already are getting closer and closer to the form of generating functions that we want. In fact, we are there because we have n equals 0 to infinity, and you have x to the n. Now, what is this entire sequence of multiplications? Well, this is the definition of a combination. In fact, this is in particular the definition of a combination n plus k, choose k. And you can verify this for yourself by looking at the definition of the combination in general and plugging this in and confirming. So what we ultimately get is that from where we started from, which is 1 over 1 minus x to the k plus 1 power. So you have 1 over 1 minus x to the k plus 1. Then that's equal to the following sum. The sum, as n goes from 0 to infinity, write a better summation. There you go. N goes from 0 to infinity of the following combination as a coefficient, n plus k, choose k, x to the n. So there you go. We have just found the generating function of this iteration. But remember that in the beginning, I actually kind of wanted 1 over 1 minus x to the just kth power. But that's no worry. All we got to do is shift the k plus 1 to the right. So then we just replace k with k minus 1. So that over here we get 1 over 1 minus x to the k. And then we just replace k with k minus 1 over here. So it's n plus k minus 1, choose k minus 1. And this is what I actually was hiding up here, right over here. This is the result that we can see. I'm going to reproduce this right over here. Like this. So typed out nicely if you want to see it over here. We derived, using the kth derivative of the geometric series, the following pattern. That 1 over 1 minus x to the k plus 1 power is going to be the sum as n goes from 0 to infinity of the following coefficient, n plus k, choose k, x to the n. For some fixed k, that is an element of the non-negative integers. So k is in integers greater than 0, because that's how we're doing derivatives. And you can verify for yourself that when you take the 0th derivative, as in 1 over 1 minus x to the 0 plus 1, you can just get the geometric series right here. And once again, if you want to get 1 over 1 minus x to the kth power strictly, you just shift everything so you get k minus 1 instead. So that is really cool, because we just saw this connection with the geometric series in particular, that the convolution of it with itself multiple times is just a perturbed version of its derivative with multiple times. And so this is a very special property of the geometric series. Once again, we just discovered another very interesting fact about the geometric series, the hero of our story. Now, you might see a connection here with the binomial theorem, and that's what I have over here, the binomial series. And I want to make sure to say a couple of notes about this before we conclude. First of all, I want to stress the importance of not conflating these two qualities. That fact that 1 over 1 minus x to the kth power has the coefficient n plus k minus 1, choose k minus 1, while the binomial series has k choose n with the powers. And so you see that the n term here, which is dependent on the summation, is actually going to be the denominator-ish. It's not really a denominator, but we can call it the denominator of the combination, while it's the numerator in this term. But there are similarities here. Could there be a connection or a way in between these two? Well, that's going to be what we look at in the next episode. And we'll also explore the similarity between this generalized geometric series power expression, generating function, and the binomial series. And then we'll also take a look at how generating functions will solve complex problems in combinatorics, which is the study of counting, because sometimes it's not easy to count certain things. And we'll see how generating functions help us do that. So I hope you enjoyed this episode on the discrete convolution, and we will see you in the next one. Till then.